Okay, today we begin with the second lectures about Codimension foliations with pseudo-effective conormal bundles. We recall some materials from part one, from which we will also borrow notations. So recall that we are dealing with a priori Codimension distributions, which are defined by a twisted form. Where is the twist is given by a line bundle, a dual of line bundle, which is pseudo-effective. And it turns out by domain integrability criterion that this distributions is indeed integrable. So when we set D equal F foliations, of course. So the most simple example of such form is given by form twisted by minus D. In other words, omega can be regarded as holomorphic one forms, and the underlying line bundle L equal to D is obviously pseudo-effective and can be represented by the integration current D, okay, along D. And in this case, integrability directly resorts to the D closeness of omega. Which simply can be very simply obtained by a Stokes theorem, essentially. And okay, so we are going to consider the most simple case, which is this case, the foliations defined by holomorphic one forms. And for this, we will review very classical constructions in this setting, namely the constructions of the Albanese torus attached to any compact Kähler manifolds. And this goes as follows. So we have, so by D closeness of one form, we have natural map of the space of holomorphic one forms to the first cohomology group, whose value in C. Indeed, by Hodge decompositions theorems, the space of one form has half the dimensions of the H1. And we have also a natural map, which goes to the torsion free part of the first homology groups, to the dual of the space of one form, simply by integrations of one form along loop gamma. Okay. So as a sequence of our theory, the image of these morphisms is a co-compact lattice in the dual, the one form. So we can consider the quotients, which will be denoted by Albanese of X. And because this gamma is a co-compact lattice, free abelian groups of rank equal the dimensions of holomorphic one form. The quotient is the compact torus. Will be called the Albanese torus of X. So we get also natural morphisms from X to the its Albanese torus, simply by fixing the base point x0 in X and consider the integration of forms on paths starting to x0 and ending at x, small x in X. So when varying small x, this gives these morphisms. Okay, so if one takes those looks at the constructions above, you can easily convince yourself that one inherits from morphisms given by the pullback of the Albanese map from the space of one form, the Albanese torus, to the space of one forms in the original variety, the original manifold X. And that this morphisms is indeed an isomorphisms. Okay. So in particular, the level of foliations, if when consider one form omega on X and the corresponding foliations, these foliations is nothing that the pullback of linear foliation on the torus. That is linear foliations, linear Codimension 1 foliations. That is a foliation given by a translation of a Codimension 1 subgroup. And of course, you have to pay attention that this Codimension 1 subgroup is not closed in general. In general, it's something which is dense. In particular, one can obtain foliations on X given by holomorphic one forms and having dense leaves. Okay. Okay. So on the other hand, there exist simple criteria which guarantees that such foliations have a closed leaf that is given by vibrations of X onto a curve C. This is a very classical theorem of Castelnuovo-Desfranchis, whose statement is the following. So consider two holomorphic one form, omega 1 and omega 2, on X compact Kähler, as linearly independent of a C, but we are meromorphically dependent. Means that the wedge products between omega 1 and omega 2 vanishes. So omega 1 and omega 2 defines common foliations, that is F. Conclusions of the theorem is that the foliation F is indeed given by vibrations, it's tangent in vibrations F of X onto a curve C. And these curves C are necessarily genus greater or equal to 2. And the proof is rather simple. I will give it. Okay, so from the fact that the wedge product of omega 1 and omega 2 vanishes, there exists non-constant meromorphic functions F, which relating omega 1 and omega 2, non-constant because these forms are assumed to be independent of a C. And now we can invoke the decloseness of omega I, and this easily implies that df, the wedge product of df by any omega I is equal to 0. Okay. Moreover, because the omega I can be expressed locally as a differential of holomorphic functions, one can easily see that f has no indeterminacy points. Of course, this f as a map of X to P1 has no connected fibers, but by taking the strain factorizations, one get the situations where the foliation is defined by the morphisms on X onto C with connected fibers. And from the connectedness of fibers, it is easy to infer that the form omega 1 and omega 2 are obtained by pullback of form on C. Of course, and this implies from the C independence of omega 1 and omega 2 that the genus of C is greater or equal to 2. So one can make further observations. The fact that considers two forms which are C independence, which define the same foliations, F means exactly in this context that the space of sections of the conormal bundle to F has dimensions at least 2. And other observations that we state for further use is that if one considers free holomorphic one forms, so defining the same foliations, and so particular, we have this dependence relations between omega I and omega I plus 1, where the fi are meromorphic functions. Then, of course, because the fi defines the same foliation, we get these relations, df1 wedge df2 equals 0. In other words, the form df1 and df2 are meromorphically independent if one prefers by Siegel theorem the degree of the field generated by f1 and f2 is less or equal to 1. So I'm sorry. So yes, I apologize for this typos. This is not certainly not the last one. Okay, so one can slightly generalize the statement by the use of dimensions. So I will call briefly what it is. So something which is defined on many line bundles, complex manifolds. So collider dimension somehow measures the growth of plurisections for line bundle. That is the dimensions of sections of successive positive power of L, and it can be characterized as follows. So we consider the weighted ring RL, where each summons it's the space of sections of positive power of L. It has a natural structure of a graded ring. And of course, when we can attach to these rings the field of fractions to L, and with this in ends, one can define what is the general dimensions of L. It is simply the transcendence degree of this field QL whenever there exists a positive power of M, such the corresponding space of sections is non-trivial, and otherwise one sets KL equal to minus infinity. So from Siegel theorem, we can see that color dimensions of line bundles is necessary less or equal to the dimensions of the manifolds, and of course equality holds if L is ample. More generally, when equality holds, the line bundle is said to be big line bundle. Okay, so with this ends, one can state Bogomolov theorems, which is our generalizations of Castelnuovo-Franchi theorems. This is the following. Yes, here we consider compact Kähler manifolds and twisted forms, omega, non-trivials. So one knows such an object defines codimension distributions. Then, as a conclusion, is that L cannot be ample, except when the Anton manifold is a Riemann surface. And more precisely, the Coloride dimensions is necessarily less or equal to 1. Moreover, when equality holds, this distribution is actually integrable and even given by vibrations of manifolds onto a curve. So I will roughly explain the proof without giving much details, but it's rather easy. If the Coloride dimensions is greater or equal to 1, so one can indeed suppose up to passing to some ramified, some finite ramified covering. Well, this is the so-called ramified covering trick. I can suppose that the dimensions of the conormal, the section of the conormal is greater or equal to 1, and can conclude simply by applying Casanova-de Franchi theorem. Okay, and the strict inequality cannot occur because of the remark I've made before, which is this second point, this remark here. Okay, which stipulates that the concentrated degree of the field generated by F1 and F2 is less or equal to 1. Okay, so let's go on. Yes, so I would like to evoke problems of abundance. So I will not give the strict definition of what is abundance, but I will illustrate questions by some examples. Firstly, by remarking that if the color dimensions of line bundle is non-negative, so by definition, it implies that exists a positive power of M such a space of section is not trivial. So for M positive, of course, this implies that the L to the power M is pseudo-effective because it has sections. And so L is also pseudo-effective. Okay. And from these observations, it's so natural to ask, formulate the following. So does there exist an example of Codimension and foliations, such which violates the abundance principle? And that would mean in this setting that foliations with pseudo-effective conormal, but such a conormal as minus infinity as color dimensions, which means that there does not exist any positive power of the conormal admitting a section. So typically, manifestations what is called the non-abundance phenomenon. And the answer is yes. And these examples arise quite naturally and can be derived from the following examples. This example is be described as follows. So take X, the quotients of polydisk, n-dimensional polydisk, by torsion-free compact irreducible lattice. Such objects exist, and one sees that X carries naturally n codimension 1 foliation Fi, which I could call tautological. Those are precisely the foliations on X whose lift the polydisk is defined as the level, the kernel of dzi. Okay, Zi is the standard coordinate on the polydisk. In fact, this is due to the fact that such lattice acts diagonally on Dn. We have taken a lattice which lives in the neutral component of the automorphisms of the polydisks, and it is known that this component of the identity is reduced to the product of n copy of the Möbius transformation groups of the disk. And from the irreducibility of the lattice, one can also infer that these foliations are minimal. that is the leaves as dense. Okay, this is due to the fact that lattice, the actions of the lattice on each factor, the polydisk, is dense, as dense image. Okay, so fix one of these foliations, F1. So I can observe that F1, of course, is characterized as the kernel of dz1, but this form dz1 does not descend from the quotients. And on the other hand, it is also defined as the kernel of this solid-positive 1-1 form, eta, namely dz1 wedge d bar z1 over what is written. And so recognize the point carré métrique, more exactly, is the area form of the point carré métrique. And in fact, this form descends on the quotient x because I recall that the actions of gamma on the factors, in particular on the first factor, is given by transformation groups of the disk, which preserves the point carré métrique. So from by virtue of the property of the point carré métrique, namely the fact that it has a -1 curvature, this matrix, this transverse matrix, and used on the foliation F1, a metric with negative curvature on the normal bundle of F1, by duality, induce a metric of positive curvature on the conormal bundle. In particular, the conormal bundle is semi-positive, and in particular, pseudo-effective. So we are left with transversely hyperbolic foliations. It's simply reformulations, the existence of such a matrix. And this can be reformulated as follows here. So F1 is equipped with a transversely hyperbolic structure. That means that one can collections of local first integrals, which are said to be distinguished first integrals. Fi, such as Fi are local, Fi glue together following Mobius transformations of the disks, and Fi are nothing that original submersions of given Zi. Okay. And actually, we can recover I'm not sure. Yes, Fi by I can recover Z1. Sorry for Fi by composed by the local inverse of the projections of standard projection of dn onto the x, which is the quotient of dn by gamma. Okay, so so it turns out that this foliation satisfies non-abundance principles. I've seen it is foliations with pseudo-effective conormal bundle. And, it turns out that the color dimensions of this conormal is -infinity, and the reason is rather simple. Indeed, suppose contradictions that F1 is defined, but the color dimension is non-negative. So this means that, well, in fact, this means add to taking finite from Fi covered, but we consider very simple situations where F1 is directly defined as by holomorphic one form psi. Okay, so this one form psi is closed. So locally, it's a differential of holomorphic functions. And one remarks that that F then comes equipped with two transverse structures. On one end, the original transverse structure, transversally hyperbolic structure, and the other end, something that which is somehow transversally translation structures, okay, given by the Fi. So we can keep in mind that the small Fi and the Fi are local first integrals of F, so are function defined on the local space of leaves, so function for one variables. So it makes sense to express the local first integral small Fi with respect to capital Fi, and to take the Trojan derivative, and by applying rule of Trojan derivations, we can easily observe that the Trojan derivative of small Fi with respect to capital Fi produce a non-constant meromorphic first integral of our foliations. Of course, this is not possible because we have remarked previously that F1 was minimal foliations. It is we are dense. So one could avoid this use of the Trojan derivative because the manifold here is very explicit. But here's the advantage of argument work in the more general setting, as we will see later. Okay, so another question, which is also related to abundance problems. Consider, say, omega, homomorphic one form twisted by a flat line bundle. The Keller setting, this means that the first real chain class of L is equal to 0. The question is, does this imply that L is torsions? So it is related to abundance phenomenon because L is torsion. This setting means that the colorized dimensions is equal to 0. Okay. And obviously, the answer is in general negative. The typical example are given by Riemann surfaces, genus greater or equal to 2. One can easily produce, for instance, by Riemann-Rohr, this Riemann surfaces, such objects, holomorphic one forms, twisted by flat line bundles, which are not torsion. Of course, this one form has to vanish somewhere. Vanishing locus here consists of finitely many points in the case of Riemann surfaces, because the canonical bundle of such surfaces is ample. But if one removes this, in general, if one removes this codimension 1 vanishing locus, the answer is positive. And so more precisely, it's the following statement that assumes that the vanishing locus of omega has at least codimension 2. That implies automatically that twisted line bundle, the twist line bundle, is torsion. And moreover, if L is not torsions, then it can't occur only when the codimension, the vanishing locus of omega has codimension 1. One can assert that the foliation F is defined by omega is given by fibration onto curves. More precisely, the omega is nothing but the pullback of four-bond curve satisfying this property above. So I will not explain why it is true, but only mention the ingredients. This essentially relies on the property of the so-called green Lazarsfeld subset combined with the Lin semi-simplicity theorem. And of course, when the codimension singular locus is at least 2, observe that this means precisely that alpha, more exactly L star, is the conormal bundle. One can summarize this by saying that the vanishing the chain class of the conormal bundle implies that this letter is torsions. So this is exactly the opposite phenomenon we have observed in the case of the question of polydiscs. The case where abundance holds. It is vanishing, the numerical vanishing. This equality corresponds exactly to the vanishing of the colored dimensions. So there is a natural questions. Indeed, the main object of this lecture. The following: can we give somewhat reasonable prescription classifications, Codimension foliations, with conormal bundles does not satisfy the abundance principles. So this means, from the previous observations or theorems, that can we describe foliations that the conormal is pseudo-effective and with such that the cholera dimension of the conormal is minus infinity. So we have seen previously that such example exists. Examples of the quotients of the polydiscs. And it turns out that there is an answer where the quotients of polydiscs are precisely involved. And the statement is the following, and I will explain notation in a few seconds. This is the main theorem. So consider Codimension foliations and projective manifold. I guess that the result still holds true in the Keller case, but I don't know to prove it. So the ambient manifold is assumed to be projective when so. So suppose that the conormal is pseudo-effective and has cholera dimensions equal to minus infinity, then one can assert that there exists a morphism phi of X and the compactifications of the quotient of the polydisc by lattice, such that F is the pullback of one of the tautological foliations we have defined below. So what are the notations? So as I say, gamma is an irreducible lattice of the natural component of the identity of the automorphism groups of the polydisc. And the superscript BB denotes the Belli-Borel compactifications, which is general constructions for quotients of symmetric space. In this section, this consists only in adding finitely many points, which are called cusps. Actually recalls that gamma is only a lattice, so it's not necessarily a co-compact. There's only a finite covolume. And as I say also before, Fi is one of the tautological foliations. So defined by the kernel of dzi, which on the polydisk, which descends on the quotients by diagonal actions of gamma on this polydisk. Okay. Actually, it should be mentioned that in our setting, which means that with pseudo-effective, only pseudo-effective conormal, non-logarithmic version of the positivity of the conormal, the Bailey-Borel compactification is irrelevant in the sense that what can prove that the image of phi lies in the no compactified phi locus of quotients. Image simply lies in the quotient of dm by gamma. And I have also some additional observations. So I evoked logarithmic versions of the theorem. It exists. And I will not develop more further this aspect. But in this setting, it is quite natural to take the Bailey-Borel compactifications. For instance, foliations with logarithmic pseudo-effective conormal bundle arise naturally when considering a smooth projective model of the Bailey-Borel compactifications, so-called toroidal compactifications. And one can also observe that somehow this manifold, or more exactly this variety, normal projective variety, plays an analogous role to the Albanese torus when the code-array dimensions of the conormal is non-negative. In this case, I recall, well, say when the conormal has sections which can be realized in taking finite ramified curves, the foliation is defined by the one form which came from torus. This is the Albanese constructions. Okay. So I would like to end up by briefly unveil the ingredients, the proof. We'll address the points in the following and last lectures. This consists in essentially 2 points. The first point is to construct from the pseudo-effectiveness property, construct transverse invariant matrix, parabolic, which has the properties, in fact, of the transverse invariant matrix attached to the tautological foliations in the quotient of polydisks. And so this can be realized thanks to the proof of the Bailey theorem. In general, one can define this metric X itself because there are some degeneracy properties along some certain hypersurface H. And from this transverse hyperbolic structure, one inherits morphisms of the fundamental groups of the complement H of X into the Möbius transformation group of the disks. This corresponds to the so-called monodromy representations, foliations, equipped with these hyperbolic transverse structures. And once we have these representations, we are going to prove that this is the rigid representations. And to conclude, one can exploit deep results by Corrett and Simpson for free to conclude that that we are done essentially, that the foliations came from pathological foliations and the questions of polydiscs. Okay, so this concludes the second lecture. See you soon.